many of you may know, like Spark SQL is the framework that powers and optimizes the applications in our unified analytics. So one of our major focuses at Databricks has been improving the performance of Spark SQL. And cost-based optimization, aka CBO, is one of these improvements. Released with Spark 2.2, what makes CBO different from other Spark optimization is that the optimization decisions are based on planned costs, which are inferred from statistics. So some of the cost-based optimizations include, what we have here is like join reordering, like join strategy selection, and like shuffle push down in our Databricks runtime. And but to enable CBO, users have to kind of need to run a SQL command called analyze table to collect the stats before running queries. So while CBO is definitely a big step towards a more mature and more sophisticated query optimizer, it has some limitations too. So first of all, is this like manual effort for your stats maintenance. So it's just to say that it requires users to manually collect the stats and keep them up to date. And the overhead of such stats collection is not is like cannot be overlooked. And second, even if all the effort has been taken to ensure the completeness and updatedness of the stats, CBO might not work well with like complex per plan structure where the cost estimation can easily go wrong, or with predicates that have UDFs, like user-defined functions, and cardinality of such predicates is impossible to evaluate. And now in Spark 3 and Databricks Runtime 7, we have introduced adaptive query execution in order to address the issues we just talked about with static stats and static cost estimation. So adaptive query execution, or what we also call AQE, performs iterative query re-optimizations at runtime based on runtime stats we collect during the query execution process. So unlike static CBO, AQE can also work with tables that have no stats, or tables that have sales stats, or queries containing those hard to estimate predicates. But it's worth mentioning that AQE is not meant to be a replacement of CBO. There's been some misunderstanding that CBO is no good, CBO is out of date. That's not true. Actually, AQE builds on top of and takes advantage of the CBO framework. So it aims to be an extension of CBO, as it re-evaluates the decisions made at runtime, made at compile time, and adjusts them if necessary, or sometimes makes new decisions impossible to make at compile time due to insufficient query infer or stats. So this is an overview of what kind of optimizations AQE does now or can do in the future. So first of all, it's this join strategy adjustment. So say if something like a join has been planned as a SORMA join at compile time, we'll revisit this decision and see if it can be switched over to broadcast join. And then it's this skew join detection and optimization. AQE is in a unique place to do this kind of optimization because it knows at runtime the exact size of each partition and can figure out easily which partitions are actually significantly larger. And then the shuffle partition number adjustment, we pick the best shuffle partition number for the query. And then there's other optimizations we can do, like empty relation propagation or join reordering, which is yet to be implemented, or other logical optimizations that depend on like runtime stats or query info. Before I switch over to Allison, who will give you a presentation of the details of how AQE works with a notebook demo, I'll quickly show you the performance numbers we got on TPC-DS benchmark. So out of the 99 queries, the TPC-DS benchmark, 32 of them had more than 1.1x speedup. And the most improved query, Q77, had over 6 times speedup. And it's interesting that, like the TPC-DS benchmark doesn't have data skew at all. So the benefits we're seeing here, the improvements we're seeing here, have merely come from, joint strategy selection and partition coalescing, like the partition number, like readjustment. And then with queries that do have data skew, we've seen like huge improvements coming from the skew join optimization. Well, that's the, that's all I have today, but let's just switch over to Allison, and she'll show you a very nice demo today.
Thank you, MaryAnn. Cool, I will share my screen now. Can everyone see my screen?
Yep.
Looks great.
Perfect. Perfect. Hi, everyone. Thanks again for joining us today. My name is Allison. I'm a software engineer at Databricks. And thanks, MaryAnn, for a very nice introduction for AQE. And today, I can't wait to share with you guys all these cool features that AQE can do with this demo notebook. So I downloaded this demo notebook from one of the earlier blog posts from Databricks for adaptive query execution. And feel free to check it out with the blog link. And hopefully in today's session, you can get a better understanding what exactly is AQE and why it can make your query faster. So before we start, a major announcement here. Since we last time announced AQE in the Spark AI Summit mid this year, AQE has been enabled by default in Databricks runtime 7.3. So if you're using any version that is 7.3 or above, you no longer need to turn on AQE by AQE. So it's turned on by default, and it's very easy to use. And 3 major features, as MaryAnn mentioned earlier, for AQEs are coalescing the shuffle partitions, switching join strategies, and optimizing for skew joins. And if you want to know more, here I have included a few more resources here that includes 2 of our blog posts and a more comprehensive guide for AQE. Great, let's dive into the demo session. So let's try it out to see if AQE is actually enabled here or not. So we can see that the adaptive enabled value is true because I'm using an image that is 7.3. Perfect. So before I get started, we need to create some tables here. So for the demo reason, I've already created a table, and it took some time. It took 7 minutes to create a table. So I already ran it before. And here we can see that there are actually 2 tables created over here. So the first table is the item table, which consists a item with item ID and an item with a price. And the second table is the sales table, where it has a foreign key that linked to the primary key of the items table. And it has the quantity of the sale and the date of the sales. So note here that in the comment of the notebook, we got a sales table created, and the item with the item ID 100 actually accounts for 80% of all the sales. So the table is actually really skewed. This is for the demo purpose, or later that we'll show you for how AQE can handle the skew join in the tables. So let's go on to check out the schema. So if we check out the schema for items, yeah, we got the item ID and price, and we see the schema for cells. We got 3 columns, and we check out the data distribution here. We see that indeed for the item with item ID 100, we got 80% of the 1 billion rows to be this item in the sales record. Awesome. Let's move to the first optimization for AQE, which is coalescing shuffle partitions. So if you ever used Spark before, you will notice that tuning the shuffle partition in Spark is really hard. If you set the value to be a small value, and it can cause like GC issues. If you make it too big, it will lead to a lot of tasks being created and have very inefficient I/O operations. So how can AQE actually help us over here? AQE can actually coalesce the small partitions and make the number of tasks smaller to speed things up. Let's see the effect of AQE in action over here. So here, the query that I got is getting the summation of all the cells quantity grouped by the cell state. So let's see how the query ran without AQE. Cool. So first of all, we noticed that the query took 8 seconds over here. And if we open the Spark jobs tab, we can see that there are 2 jobs being created. And the first job has 2 stages. The first stage has, let's see, 32 tasks. And all the subsequent stages follow here have 200 tasks. And why there are 200 tasks? That's because if you recall this 200 magic number here, it's because that's the default shuffle partition number that Spark has. So which means whenever after the first, so the first task is the number of task partitions created when you're scanning the data. And this number depends on the size of the data. And after you move on to the next stage, you see that there's 200, which means Spark always creates 200 tasks for the shuffle operation. And let's see how the query plan look like when we have 200 tasks. Is it actually necessary? So let's go to the query plan page over here. So a query plan is a visualized way that you can see how Spark actually runs the query. And if we scroll down over here, that we notice the exchange node over here. So the thing that we want to focus on is the shuffle bytes written total. And we notice that there are, the shuffle bytes is really small. It's only 417 kilobytes, which is even less than a megabyte. And if we scroll down again, for another exchange node, it's only even smaller. It's only 22.4 kilobytes. So we're shuffling the data with 200 tasks for data with size even less than 1 megabytes. It seems to be not very efficient over here. So I would decrease the shuffle partition number to make it more efficient. But tuning the shuffle partition number is difficult. So how can AQE help us here? So if we enable AQE and run the exact same query, first we expand the number of Spark jobs over here. So first we see that the number of jobs actually increased. Shouldn't AQE be faster and but we do see that there are more jobs. And also that we see there are a lot of stages that have a note over here called skipped. Hey, MaryAnn, so I'm curious, what's happening here?
Yeah, that's a very good question. So I think quite a lot of users might have just noticed this, this phenomenon as well. When they turn on AQE, there's usually more number of jobs, versus when you have AQE off. Like basically, like what happens is like what used to be just like the stages in the jobs with non-AQE. Now turns into individual jobs. So that is to say, with non-AQE queries, you tend to have multiple Spark stages under one job. So you have have smaller number of jobs. But with AQE turned on, it's like almost like one single stage, mapped to each job. So it's roughly, I mean, just, most of the cases you will see the number of all stages with non-AQE is equal to the number of the jobs. And the escape stages is part of, the Spark core, which means, the stages that have been completed in previous jobs. So they can just basically be ignored. Yeah.
Got it.
In the meantime, whatever it is, whether it's a job or a stage, it doesn't really matter to your query running time. It's the same amount of work, but just categorized differently.
Got it. So this doesn't necessarily mean that there are more stages being created.
Yeah, exactly. Yeah.
Got it. That makes a lot of sense. Also, I noticed that here, instead of having 200 partitions as the default setting for number of shuffle partitions, the number of tasks here decreased to only 1. That's very interesting. Let's see what's going on by viewing the Spark plan behind AQE. So here we got the Spark plan behind AQE. So first, let's check out the exchange. So the exchange actually have very, again, it's very small amount of data shuffled. Let's compare it with the plan that we got when we disabled AQE. So the exchange over here is very similar. And notice that we got a new node added after the exchange, which is called custom shuffle reader. If we expand this node, we can see that this custom shuffle reader actually has 2 metrics. One is the number of partitions, which equals to 1, which happen to be the number of tasks that created, and the partition data size, which is actually the size of the partition. So the magic behind AQE over here is that the custom shuffle reader over here actually coalesced small partitions during the exchange, and it coalesced partition into only one partition so that the number of tasks can decrease from 200 to 1 and subsequently speed up the entire query process. That's a very interesting concept. So I see that the custom shuffle reader here actually coalesced the small partitions. And if I hover over the exchange node over here, and it still have a number 200, which means the number of shuffle partitions actually didn't get changed. And let's see the exchange node after the custom shuffle reader, which is also 200. So MaryAnn, so I'm curious, does AQE actually change the shuffle partition number? Can it actually like decrease or increase the shuffle partition number, or it's only using the custom shuffle reader to coalesce the smaller partitions?
So we've got this question multiple times as well. So it's important to understand that AQE itself does not change the shuffle partition number, or what we call the initial partition number. So it's like on the map side of the shuffle, it's just kind of the shuffle does, mean, it just splits data into 200 buckets for each mapper, right? And then in the end, all AQE does is kind of combine the small partitions together. But at Databricks, in Databricks runtime, like in this version too, like in Databricks runtime 7.3, we also have a functionality called, like a feature called AOS, Auto Optimized Shuffle, which does what you just mentioned, that can increase or decrease the initial shuffle partition number according to each stage. So combined with AQE together, the two features working together, it can just kind of expand the shuffle partition number, shrink the shuffle partition number with each stage in the query.
That's very cool. So auto-optimized shuffle, does it actually change the shuffle partition number globally, or just like per query based?
It's per query and per stage, like totally depending on the data. And also that feature is also adaptive. Like, it's also part of the adaptive process, which means, like as you go along the query execution, it adjusts the shuffle partition number for the stages that haven't been executed or materialized yet.
Got it. That's very cool. Can't wait to try it out. So here is the Spark config name for auto optimized shuffle, and currently is enabled. It's not enabled, but I can't wait to try it out to see the cool effect that it can give to the query.
Yeah, we might just like start to enable it in later versions of Spark runtime, of Databricks runtime. Yeah.
Perfect. Great. So let's move on to the next strategy, next effect that AQE can do to the query, which is automatically switching the join strategies. So here I got a query that I also ran beforehand to save us time here. So we got a query that's getting the total sales amount grouped by the sales state, and for items with the price less than 10. So here's what the query look like. So when we're disabling AQE, let's see what's the runtime for this query. So this query took almost 7 minutes, and let's see what's going on here. So if we open the UI, we can see the Spark plan populated here. And as we scroll down, we notice that it's a join between the item table and the sales table, and it's being planned as a sort merge join over here. So let's see from the exchange what's going on here. So if we open the exchange node here, we see that the table, the sales table, has the data size to be almost 30 gigabytes. But if we notice over here that the items table actually only has data size to be 6.8 megabytes, which is actually smaller, if I recall correctly, which is even smaller than the auto broadcast join threshold, which by default should be 10 megabytes. But here the planner actually planned the join as a sort merge join. Shouldn't this, hey MaryAnn, so shouldn't this, why did Spark plan this as a sort merge join instead of a broadcast hash join? Because one table has clearly data size to be even smaller than the broadcast join threshold.
Yeah, if we go back to the query, we can see that like the right-hand side join table, the item table has a predicate of, a price smaller than 10 on it. And so to be able to tell eventually the filtered table will be smaller than the threshold, we need something called column stats. And what I've seen with most Databricks customers is that they don't they don't turn on column stats at all, even if they just turn on the table stats. Like probably like for two reasons. One is like collecting column stats are like, it's much more expensive, like costly than just collecting basic table stats. And the other reason is like this, you have to kind of keep track of the number of columns that you use in your queries, or you use in predicates, which columns are worth for the column stats, which are not, and that's a lot of like manual effort there. So this is and this is exactly why IQE becomes useful here, because even if you don't bother with column stats or whatever stats, it can still take effect once it finds out your query actually can be planned as broadcast has joined.
Got it. So since we're now collecting the column stats over here, the optimizer can really make the decision to plan the query as a broadcast hash join. So to be safe, it's actually being planned as a sort merge join. Got it. That makes sense. Great. Let's see how if we turn on AQE, how did the query run? So if we scroll down to here and turn on the AQE. So first of all, we notice that the runtime actually shrinked from 7 minutes to only 33 seconds. That's pretty amazing. Let's see the Spark jobs and the query plans. So if you see the query plan, the very first thing that we notice here is instead of being planned as a sort merge join, the entire query is actually being planned as a broadcast hash join instead. That's really smart. So we see if we expand the exchange over here, we see that still the two tables are very imbalanced. One is having 30 gigabytes and the other one is only having 6.8 megabytes. But AQE here is smart enough to actually detect the data size after the exchange and made a much better decision by changing the sort merge join into a broadcast hash join. So AQE avoids the very expensive execution time for a sort merge join, and instead choose the broadcast hash join over here that give us a lot of speed up when executing this query. That's pretty amazing. And I noticed here that we also have the custom shuffle reader after exchange, like the first case that we've talked about. So if we expand the custom shuffle reader here, I noticed that instead of so number of partition actually decreased also from 200 to 32. But one thing that I'm curious about is, so here, instead of having coalesced as a tag alongside with the custom shuffle reader, it's actually showing a local custom shuffle reader here. So what is a local custom shuffle reader?
Yeah, so here, so if you are, this is a runtime broadcast join converted from a sort merge join. So you can see that the map side of the shuffle work has already been done, like the materialization of the shuffle has been done. So but once it becomes a broadcast hash join, the shuffle is useless. So we don't need the result of the shuffle at all, but since it's been materialized and we cannot undo that, right? We cannot save the time from just undoing it, but still there's a little bit optimization here, which kind of reads the shuffle blocks from your local node instead of just reading over the network. So that's why it's showing a local here. So instead of doing a full shuffle, it's just doing something we call a local shuffle. Yeah.
Got it. So it actually reads the data locally, and which can actually speed up the query.
Yeah, exactly. Save some network IO here.
Great. That's awesome. That's pretty amazing. And so the very last effect that AQE can do is dynamically optimize the skew join. So here is the query that we can see. It's getting the total sales amount and grouped by the sales state. So if we recall correctly earlier when we're creating the sales table, it's actually a very, very skewed table where 80% of the records concentrate on one item ID, which is 100. So here we're joining two tables on this item ID. Let's see what's going to happen when we run the query with AQE disabled. So if we see the Spark UI for the Spark plan of this query, we can see that this query, so first of all, we can see that this query took almost 8 minutes to execute. And the plan is very similar to the plan that we saw earlier. So let's see what's going on by expanding the exchange node. So one thing that I noticed here is, so the remote bytes read total, which is 7.2 gigabytes, but the distribution seems to be very, very skewed. It has the minimum and medium to be around 11 megabytes, but the maximum is 5 gigabytes, which is a lot larger than the mean and the median. And compared to the items table, that you got a more evenly distributed data for the remote bytes read, mean, medium, and max. So let's see how this having this maximum to be so large can impact the performance of the query. So if we go to the stage, it will show us all the executor and their status in the stage page. We scroll down and we notice that here we see that the executor with ID 2 took 7.1 minutes to execute, while the rest of them, if we sort by the duration, while the rest of them only took like 4 seconds, 3 seconds, and 1 second. So we know that this executor must be running the query, the task, with the very skewed join key, which is the ID 100. If we scroll to the right a bit more, we see that compared to the rest of the executor, this one has a spill in memory to be almost 13 gigabytes and spill in disk to be 5.7 gigabytes. So MaryAnn, how can this spilling in memory and disk impact the performance of the query?
Well, yeah, so that's actually this spilling usually hurts the performance like really badly. And the more, the more you spill, the more, like slowdown you will get in your query. And what this spilling means is, like, for example, there was a lot of operations, like a few operations in Spark, which actually, if the temporary result cannot fit in memory, it just spills to disk. And later on, when it just, when it comes to the next stage, it had to kind of read from disk again. For example, like in the sort merge join, of course, you have the sort operation, right? If the sort is skewed and you get a huge partition, right? Or if it's under partition and all of your partitions are big. So within each partition, it's doing an external sort. So it's kind of like spilling out the temporary sort result onto disks, and eventually, like, it's going to do a merge among all these temporary results. So the bigger your data is, the more, the more, kind of temporary bits of spill you will get on your disks, and the more work later on for the merge to do. Yeah.
Got it. That's why it takes almost more than 7 minutes to actually execute this query, because it has a very large amount spilling in disk and memory. Let's see how AQE can help us here. So if we run the exact same query with AQE enabled, so first it took 1 minute compared to what it's earlier that took almost 8 minutes. So it must be, it gives us a lot of speed up when we run the same query. And if we go to the Spark plan in the UI, and compare it with the plan that we have seen that's when AQE is disabled. So very first thing that I noticed is, so you can see that the sort merge join node, instead of a normal sort merge join node, you actually have a tag which is skew and set to be true. So if we expand this sort merge node and expand the two nodes that's right after the exchange node, we can see that the left-hand side of custom shuffle reader, instead of just give us the two metrics here, it actually gives us 4 different metrics. And the two metrics, additional two metrics are tells us the number of skewed partitions and the number of skewed partition splits. So which means over here, the custom shuffle reader actually detects that one partition is extremely skewed and split it into 32 different smaller partitions so that it can actually help the bigger task, split the bigger task into smaller tasks and distribute them into executors to shorten the time that each executor take to actually complete the query. Let's see if that's the truth. So if we go to the query stage page over here, and we can see that sorting by duration, we can see that instead of having one executor that takes 7 minutes, we actually have a much more evenly distributed execution time on these executors and much more evenly distributed disk and memory spilling over here. So AQE detects the skewed partition and split into smaller partitions so that each executor can have a much more evenly distributed task amount and task size so that it can actually speed up the query. That is a very, very cool effect. So the very last effect that I want to show you is the empty table propagation. So here is a query that's getting all the sales quantity grouped by date. But instead of having but we are adding a condition where we're querying the items with item ID less than 0, item price less than 0. So as we know that there shouldn't be any item with price less than 0. So let's see, so the table should result in empty. So the result should be empty. But let's see what's going on when we run the query with AQE disabled. So for here, we see that the query plan is very similar to what we have observed before. So since we expect the items table to be empty, we can sort of see from the stats here. So the filter has 0 output rows, the exchange has 0, all 0. We got a exchange here, all 0, and final exchange 0, and sort is 0. So basically the entire query should return, should be empty. So let's see how long it took. It took almost 5 minutes to get the results from all the empty tables. That seems to be a little bit longer. So let's see how AQE can actually detect the fact that the table for item is actually empty and be able to optimize the query a lot more. So here is the plan for AQE enabled. And first of all, it took less than 20 seconds to run the entire query compared to 4 minutes that we got before. And if we go to the query plan over here, and we can see that it's surprisingly small. There is a local table scan and followed by a adaptive Spark plan. So AQE is very smart enough to detect that the right-hand side of the join, the items table, is actually empty. So it propagates the empty table up to the tree and finally return the empty table at the end, at the root of the query tree. So if you're curious about what the plan look like in the very beginning, or how does the plan look like without the AQE optimization, you can click the details and scroll down to see that the physical plan for adaptive query, it has a final plan, which tell you what is the final AQE plan output. And it also has an initial plan that tells you what the initial plan looks like before AQE optimization kicks in. So the initial plan corresponds to the plan that we saw when AQE is disabled. So it's very cool effect over here. Yeah, that's the end of the demo, and hopefully this give you this makes you more excited about AQE, and highly recommend you to try it out because it's really fun and it can actually speed up a lot of the queries. Cool. I guess we have 10 minutes left. Yeah, we can take questions now.
Perfect. Well, thanks very much, MaryAnn and Allison. That was really insightful, and diving into the details and the internals of AQE is really, really cool. So hey, quick question. We've got some questions here. Would you like me to ask them, or because we did prop them into a doc, MaryAnn, you can ask them yourself? I'm completely cool either way.
Yeah, so I'll just take questions, like, I'll just read the questions and answer them, like if we have time to cover all of them.
Sure.
Yeah, so I'll start with the ones that are kind of have short answers first, okay? First one is, someone asked, is AQE only available in Databricks runtime? AQE, most of it, like most of the things we have presented today is actually available in open source Spark too. But like I have to point out that AOS, like auto-optimized shuffle specifically, is only available in Databricks runtime. And the second one, someone said, like the tables used here are Parquet tables, and any delta table nuances like optimized skipping index and stuff that would conflict with AQE, the answer is an absolute no. So there's nothing conflicting between a delta tables, and it's kind of a like a little mistake we made today, just demoing with Parquet tables instead of delta tables. So like delta tables, like all the optimizations of delta tables right now are static. If we ever have any dynamic optimization we would like to add for delta tables, we could also take advantage of AQE and put these optimizations into AQE to further optimize delta table. But just just put it in a simple way, there's no conflict. There's might be like opportunities to leverage both. And then the next one is Photon engine intended to do the same thing to Spark engine what Spark did to MapReduce? I don't know what exactly like this question means, but what I mean, like I'll just explain what Photon does. So basically, we could look at Photon as another version of post-stage codegen in Spark SQL. So it doesn't necessarily have a lot to do with like Spark engine, like Spark core. What the question compares with MapReduce. So it has more optimization on the Spark SQL side. So it's basically like for each Spark operator, like aggregate or joins, like broadcast join, whatever join we have. So it converts it converts the operation from Java bytecode into like C++ code. What is even nicer about this is, it can leverage a lot of like hardware optimizations in its implementation. So it has and like again, it's just has less to do with Spark core, like the framework itself, and has no conflict with AQE whatsoever, because AQE sits on top of it. Like not sits on top of it. AQE is a process that drives the execution of the operators. So they're kind of in different layers. Yeah. And the third one, so the next one is AQE rebalances partitions only if it doesn't cause additional shuffles later on. There may be cases where it is useful to address skew even at a cost of an extra shuffle. For example, a badly skewed join that outputs a few rows. Can this behavior be added as an option, like in the future? I think this is a very good question with like a very good understanding of how AQE works under the hood. But yeah, so that that's actually something we've considered. We're still considering doing. So basically, it's a very it's a very likely situation where you can get a badly skewed join, and after optimizing it, like later on in a query, you require another shuffle. And then the benefit of doing like dealing with the skew or optimizing the skew will just overcome the overhead of doing an extra shuffle. It's very likely that we will have this kind of situation. So to be able to say we're willing to do the skew, even at the cost of an extra shuffle, we have to kind of again rely on something called cost-based optimizer. So we have to be able to evaluate the cost between doing an extra shuffle or doing the skew handling. So this is something that we're looking to add onto the current AQE framework. We have right now the decision is kind of simple, but we kind of wish to make it more sophisticated, adding a more sophisticated cost model to the AQE framework so that we can evaluate such conflicting options at a more advanced level. Yeah. And next one is what is the relationship between AOS and AQE? Yeah, so probably I didn't just go into a lot of details with AOS just now, but AQE is like the typical usage of AQE partition coalescing. Like I believe that this question regards to AQE partition coalescing specifically. Not the other functionalities in AQE, but to be like the typical usage scenario with partition coalescing is that user assumes that he has a pretty good idea of what to set for the initial partition number. For example, your query is dealing with like a few gigabytes or a few I don't know, like 100 gigabyte or something, like this kind of level of, like data size. You would have to kind of spin up the initial partition number by yourself. You would have to really understand what kind of size, data size your query is dealing with, and kind of proportionately set your partition number to something higher than 200, right? Like 2,000 or even like 20,000 sometimes. And so this is something that users of AQE still have to do manually, because AQE can only kind of just like shrink the number of partitions instead of increasing it. And then AOS steps in here to try to make the process, the whole tuning process of shuffle partition number automatic for users. So like, just, this decision of what to set as the initial partition number, if it's 200 or 2,000 or even higher, is handled by AOS, like auto-optimized shuffle. So it also decides for you what's the best number or what's the close to best number for the initial partition number, and which means it can just expand and shrink at runtime. depending on your query size. Yeah. And then I think the last one here is what is memory spell versus disk spell. Yeah, so it's not, I don't think it's off heap memory, but the memory spill is probably something like, it doesn't have to be off heap memory. So it depends on whether you turn on off heap memory. But if it's not, then it's just, like the memory space you ask from memory manager. And then usually, I mean, the memory spill can be, can be bigger if there's less, like the partition skill, like there's only one skill partitions, and then otherwise, if it can't get that much memory, it has to get everything onto disks. Yeah.
Perfect. Hey, we're running right up to the hour. So again, thank you very much, MaryAnn and Allison for the presentation, the amazingly cool demo. We've already got lots of requests for it. So we'll work on making sure to broadcast that to GitHub, Databricks Tech Talks location that Karen and myself had already sent out to everybody. And also, MaryAnn, thank you very much for tossing lots of awesome, answering all those questions so quickly. So Karen, why don't you wrap up today's show? Again, thank you very much for taking the time.
Yeah, thanks again, MaryAnn and Allison. That was a great presentation. Like Denny mentioned, we put in the chat the link to the notebook that will be available shortly. And then also I posted the YouTube link. So the recording is available now, and the link is in the chat. So with that, thanks everyone for joining us. And I hope you'll check out our Tech Talk next Thursday. And I hope everyone has a great rest of your day. Take care.
Thank you, Karen. Thank you, Danny.
Thank you.
Yeah. Bye.